In this video, we're going to learn about Stirling engines, and then construct an alpha-type Stirling engine and try extracting some useful work from it. We're then going to watch physics in action and probe some measurements like temperature, volume, and angular velocity, and finally, we're going to play around with phase angle.
A Stirling engine is a type of heat engine that utilizes cyclic compression and expansion of working fluid in a closed system using external heat. Now, there are multiple types of Stirling engines out there, but we're going to focus on alpha-type Stirling engine, in which we displace the working fluid into two separate cylinders, hot and cold. You see, the heat itself is not very important, it's the temperature difference between these cylinders. The greater the temperature difference, the higher efficiency we can achieve. The flywheel is what couples both the pistons, maintaining their phase angle, and is an integral part of the Stirling cycle. The phase angle determines by how much will a piston be ahead of the other in a cycle. In the upcoming demonstration, we're going to be using the ideal phase angle of 90 degrees. The regenerator, as pictured, is usually closely packed metal fins to increase the surface area to allow quick dissipation and absorption of heat. Addition of a regenerator increases the efficiency, and in the ideal case, pushes it as high as the Carnot cycle. Note, there is no regenerator in our model due to time, but if I were to make one, it would probably be a chamber with steel wool, which acts very similar to the metal fins. Let's analyze the cycle in slow motion. We're going to pause at 4 key steps of the Stirling cycle. The figures on the right show the position of both the pistons with respect to the flywheel, and the dotted line in gray shows the halfway point. We've paused at what appears to be step D. The cold cylinder has minimum volume and the hot cylinder is at the halfway point. The gas in the hot cylinder is now going to heat up and expand, and we will transition to step A. You can see that some of the gas in step A has leaked into the cold cylinder, but if you observe the flywheel diagram in part D, the arrows indicate the direction of force. We can see that the torque due to both the pistons are in the same direction, and so they will add up and together rotate the wheel in anti-clockwise direction. Now we're at step A, where the hot piston is completely pushed out and there's maximum volume in the hot cylinder, and the cold cylinder is at the halfway point. Now the momentum of flywheel is going to kick in and continue the next quarter of the cycle, rotating it further anti-clockwise by 90 degrees. Also notice that ideally there's no change in volume transitioning from step A to B. Step B. The hot piston is at the halfway point and there's maximum volume in the cold cylinder. The gas is now going to cool down and compress, pulling back both the pistons as we transition to part C. Now if you observe the direction of forces in part B, the torque will add up and they will together rotate the wheel further anti-clockwise. Onto the final step, C of the cycle. The hot cylinder has minimum volume and the cold cylinder is at the halfway point. The flywheel momentum kicks in and it further rotates by 90 degrees anti-clockwise. Also, once again, notice that ideally there's no change in volume transitioning from step C to D. We usually use pressure volume and temperature entropy diagrams to show the dynamics. Now if you notice from step D to A, there's isothermal expansion. That is, the gas is heated from the external source and there's decrease in pressure and increase in volume while the temperature remains constant. Also note that the entropy of the system during this step does not change. Now from step A to B, we see isochoric cooling. The volume doesn't change and the cooling is attributed to the regenerator, where the gas dumps heat into the regenerator as it passes from the hot cylinder to the cold cylinder. Note that in this step, there's a decrease in the entropy of the system. From B to C, we have isothermal compression. That is, the pressure increases and volume decreases, while the gas dumps heat into the cold cylinder without a change in temperature. In the final step, from C to D, we return to our initial state through isochoric heating. Now again, the volume doesn't change and the heating is because of the regenerator. The gas picks up heat as it moves from the cold cylinder to the hot cylinder. Note that the entropy increases in the system back to the initial state, indicating that the total entropy change in the cycle is 0. This ideal model of Stirling engine achieves efficiency as high as the efficiency of the Carnot cycle. However, figure 2 shows experimental data from a real Stirling engine, and we can clearly see that it's far from its ideal efficiency.
And now it's time to move on from the ideal world into the many hours-long adventure of actually constructing it.
I designed this flywheel to directly mount it to the axle and easily change phase angles. I also wanted it to be heavy for greater inertia. Thanks Al for the help with CNC. I've made a mistake and the wheels were not perfectly aligned in phase and they were imbalanced. I had to clean this up later because of very low tolerances in the syringe, as it would actually increase the friction. I clamped my engine down and it was now time to test. I didn't realize then that the hot piston was actually behind the cold piston. Created a heat spreader and a shield for the tube. Even after correcting the phase, I noticed that there may be an issue with alignment and friction as the flywheel does not snap to 2 stable pressure points. I redesigned the flywheel with a different attachment mechanism and lighter, as I thought the previous one might be too heavy. At this point, I also realized we could have done this with the given parts. Now that's much better than before. At this point, I thought it might be the gear in the middle that's actually concentrating the moment of inertia, so I decided to take it off. Now that looked promising. I suspect that it might be the friction in the big bearing, so I decided to swap for a smaller one.
And there you have it, a working Stirling engine. The aim in the previous part towards the end switched from making something efficient to getting something that works. And the reason is to save time for this part, where now we're going to probe some physics.
I found it to work the best when there's some amount of volume between the cylinder and the piston, and the tube is connected when there's minimum combined volume in both the cylinders. I decided to use an NTC thermistor to measure temperature. We're using Arduino and MATLAB to acquire data every 60 milliseconds. Note that the temperature readings you're about to see might not be entirely accurate because of the material properties of the probe and the high rate of acquisition and the device used. Temperature in the cold cylinder increases, but zooming in does not reveal individual cycles. At times, the piston heats up more than the cylinder, phase angles and radius. So here are the results. Note that a better analysis could have been done with the tracking software. The highest RPM is achieved at a radius of 7 millimeters, and in the case of 10 millimeters, we achieve maximum RPM at 102.5 degrees, which is greater than the ideal angle of 90 degrees. That would be all for this assignment, but I would love to pick this up in the future and explore more. Thank you for watching.